Hi, in this video we are going to see about the steady state error. If the output of a control system at steady state does not exactly match with the input, the system is said to have a steady state error. Any physical system inherently suffers steady state error in response to certain types of inputs. A system may have no steady state error to a step input, but the same system may exhibit non-zero steady state error to a ramp input. The classification of control system. Control system may be classified according to their ability to follow step inputs, ramp inputs, parabolic inputs, and so on. The magnitude of the steady state error due to these individual inputs are indicative of the goodness of the system. Consider the unity feedback control system with the following open loop transfer function, which is given g of s in this equation. It involves the term s power n in the denominator representing n poles at the origin. A system is called type 0, type 1, type 2, and etc. if n equal to 0, n equal to 1, n equal to 2 respectively. As the type number is increased, accuracy is improved. However, increasing the type number aggravates the stability problem. A compromise between steady state accuracy and relative stability is always necessary. Consider the system shown in the following figure. The closed loop transfer function is given as g of s equal to in this equation. Steady state error is defined as the error between the input signal and the output signal when t tends to infinity. The transfer function between the error signal E of s and the input signal R of s is equal to E of s by R of s equal to 1 divided by 1 plus G of s. The final value theorem provides a convenient way to find the steady state performance of a stable system. Since E of s is 1 by 1 plus G of s into R of s, the steady state error is ESS equal to limit s tends to infinity s into R of s divided by 1 plus G of s. The static error constants are figures of merit of control systems. The higher the constants, the smaller the steady state error. In a given system, the output may be the position, velocity, pressure, temperature, or the like. Therefore, in what follows, we shall call the output position, the rate of change of the output velocity, and so on. This means that in a temperature control system, position represents the output temperature, velocity represents the rate of change of the output temperature, and so on. The steady state error of the system for a unit step input is 1 divided by 1 plus G of 0. The static position error constant Kp is defined by Kp equal to G of 0. Thus, the steady state error in terms of the static position error constant Kp is given by E equal to 1 divided by 1 plus Kp. For type 2 for type 0 and type 1 system, the static position error constants are given in these equations. The steady state error of the system for a unit ramp input is E equal to limit s tends to infinity 1 by s into G of s. The static velocity error constant Kv is defined by Kv equal to limit s tends to 0 s into G of s. Thus, the steady state error in terms of the static velocity error constant Kv is given. The static velocity error constant for type 0 system, type 1 system is given in these equations. For a ramp input, the steady state error E is E equal to 1 by kV which is equal to infinity for type 0 systems, E equal to 1 by k for type 1 systems, E equal to 0 for type 2 or higher systems. The steady state error of the system for parabolic input is E equal to 1 by limit h tends to 0 s square g of s. The static acceleration error constant Ka is defined by Ka equal to limit s tends to 0 s square g of s, where the steady state error is given by E equal to 1 by Ka. For type 0, type 1, type 2 and type 3 systems, the static acceleration error constant Ka is given by these equations. For a parabolic input, the steady state error E equal to infinity for type 0 and type 1 systems, E equal to 1 by k for type 2 system and E equal to 0 for type 3 or higher systems. The deviation of the output of control system from desired response during steady state is known as the steady state error. It is represented as E. C of s by R of s equal to G of s divided by 1 plus G of s, where C of s equal to R of s into G of s divided by 1 plus G of s, E of s equal to R of s minus C of s, E of s equal to R of s divided by 1 plus G of s. When E equal to limit s tends to 0, s into R of s divided by 1 plus G of s. The following table shows the steady state errors and the error constant for standard input signals like unit step, unit ramp and parabolic signals, where Kp, Kv, Ka are the position error constant, velocity error constant and acceleration error constant respectively. An example problem is shown here. For the system shown in figure below, evaluate the static error constant and find the expected steady state error for the standard step, ramp and parabolic inputs. The problem is solved in this example. We can find Kp, Kv and Ka value and the error values for static error, acceleration error and velocity error. Summary is given in this slide. For type 0, type 1 and type 2 system, step for step input, ramp input and acceleration input. Thank you.